All right, we're looking at Unit 1 still, but we're looking at mass spectroscopy of the elements. And our goal is to be able to explain the quantitative relationship between mass spectrums and the masses of the elements, isotopes. So let's take a look at what a mass spectrum looks like. And we're going to call them mass specs for short. So this is a sample mass spec for the element boron. And we're going to break down what we see in this graph. So to start off, from the graph, immediately the first thing I know is that this is boron. It's in the title. If that title's not there, then I start breaking down the other elements. There are 2 bars, and this tells me that there are 2 isotopes of boron. The number of bars is going to tell me the number of isotopes. On the x-axis, it's going to tell me the mass number for those isotopes. So this is boron 10 and boron 11. On the y-axis, I'm going to get the percent abundance of each of those isotopes. So here, boron 10 is right about 20%. Boron 11 looks right about 80%. If I'm given numbers, great. If not, I'm going to estimate those numbers. Now, if I want to estimate the mass of boron, I can do it from this mass spec. Here's what I know. The mass has to be between the highest value and the lowest value. Sorry, that's supposed to say lowest value. So I know that it's got to be between 10 and 11. But this is a weighted average, which means the percent is important. And there's more 11 than there is 10. So I know that it's closer to 11. Matter of fact, I know that because 11 is 80% and 10 is 20%, that it is 80% of the way to 11. So I can estimate this pretty well at 10.8. It's easy when the numbers are right next to each other and there's only 2 peaks, because I'm just looking at the percents. I can also do this mathematically. I know that this first bar is a mass of 10. I know it's about 20%, so I'm going to multiply it by 0.2, 20%. The second bar is 11, and it's 80%. And I'll get that same number, 10.8 atomic mass units, which is the atomic mass for boron. Let's try a slightly bigger one. So here's chromium. Chromium has 4 isotopes. And I can see that because there are 4 peaks, 1, 2, 3, 4. Of all of chromium's isotopes, the most common one is chromium 52 at 83.789%. The other ones are very small comparatively. I can say that the average atomic mass for chromium is between 50 and 54, because it can't be lighter than the lightest and heavier than the heaviest. And I can also say pretty confidently that this peak is so large, this 52 is so abundant, that it's going to be close to 52 atomic mass units. And in this way, I would be able to identify this as chromium, because there aren't very many elements that have a mass of around 52. But here's the math for it, right? I'm just going to take each mass, multiply by its percent. I do have to make sure to convert those to percents or to decimals. And I'm going to add them up, and look at that, 52.06. The fact that this giant peak at 52 is there, I can estimate that it's going to be around 52, especially because the other peaks are going to cancel each other out, right? I have one at 50, which is 2 away from 52, and one at 54. These two are almost going to cancel each other out, because I have 4% on this side, 2% on this side. It's going to come back at 52, a little bit closer to 51, but that's fine. All right, so that is how we're going to look at these mass spectrums.